So thanks to the organizers for inviting me both to come to the workshop and to speak. So I will be speaking, in fact, neither about the modes. Okay, so I'm pretty sure that everyone knows what the mode solution is. I will not be speaking also about the quasi-normal modes. Okay, so it's also a very familiar object in the study of black hole dynamics, but I will be interested in the study of, let's say, quasimodes. So of course there will be a strong link between these quasimodes and the modes and the quasi-normal modes. So what are the modes? The modes are, say, a mode solution. That's a solution, let's say, of okay, so this is just an introduction to the ideas. I mean, don't want to be too precise, but let's say it's a solution to some sort of wave or Klein-Gordon equation, which takes a form such as, let's say, if you're in 3D, something like this, where this phi is going to be a solution to some elliptic PDE. Let's say a box of phi, let's say some elliptic operator. And what's important is that this solution is, so omega is a real frequency, and so this solution is periodic in time. Okay? And where do we find mode solutions? We find them typically for systems which are closed, when there is no escape mechanism. Okay, so this is for closed system. Okay, so if you remove the fact that this system is closed, you have an open system, okay, in which you can have quasi-normal modes. Now, there are several possible definitions of these quasi-normal modes, and in fact, I believe that tomorrow Claude will tell us more about, the different way of defining them. Let me, for the moment, just take the intuitive idea that you replace the real frequency by a complex frequency. Okay, so you now have a solution, say, of the form e to the I omega t minus st or something like this. Okay, and let me also warn everyone, just to refresh our mind, that while here typically we are in the mode solution, you look for solutions which are let's say regular. Say, for instance, they have finite energy. Okay, so they live, let's say, in a nice space, in a nice Hilbert space. In the case of the quasi-normal modes, it's not necessarily true. I mean, it depends how you will define them. So one has to be a bit careful about what do we really mean by a solution here. Okay. Now, what are the quasimodes? So the quasimodes, they can be defined. They don't really care whether it's an open or closed system. Let me also mention here, of course, that if, let's say, S is positive, then this solution will decay. Okay. Okay, so for the quasimodes, there will be, again, it's a solution like the modes. They take the same form. So let's say psi of, you see something very familiar. Okay, and omega is real here, like for the modes. But there is a big difference to the modes that actually these quasimodes, they are not solution to anything. They are only approximate solutions. Okay? So it's going to be an approximate solution. So what do I mean by an approximate solution? I mean that, say you take your original elliptic operator, then this will satisfy something such as omega squared, let's say, phi minus p of phi is equal to some error. Okay? So, of course, any function satisfies something like this. So it's only useful if this error is small in some sense. Okay? Okay, and this quasimodes, they also live in some nice energy space, okay? So the psi will belong to, let's say, some nice energy space. Now, what do I mean by this f is a small error? So the truth is that the quasimodes, it's not something that you can put singular. It's only quasimodes with an s, because it's not just one approximate solution, it's a sequence. So one should remember that, let's say, we look at a sequence of psi L of some frequency. Okay? So you will have equation, let's say, with L everywhere here. You can also make the operator depend on L a little bit, but let me not worry about this. And what you want is you want the error to go to 0 as the frequency. Okay, so you can think of L as measuring the size of the frequency in some sense. Okay, and it will also not be sufficient to just have, in most applications, you don't just want to know that the error is small, you want to know that it is small in some norm. Say, for instance, the energy of phi L, or the energy of phi L in some domain, not phi L, f of phi L. And you want also to know it with a rate. Okay? So typical applications are the energy of this object, let's say, is less than L to the minus P, with P, let's say, bigger than 0, or E to the minus L, or E to minus a constant time L, or something like that. Okay. So finally, these quasimodes have two properties. Okay, so by constructions of these quasimodes, you will see in the application that this will hold. These quasimodes, so let's say the psi L, they are going to be localized, I mean not extremely localized, but a little bit localized, both in frequency and in space. Okay? They're not going to have both compact support in frequency and space, that will not be possible, but they have some frequency and some space localization. So what do I mean by localized, let's say, in frequency? I mean that, for instance, if you think of, let's say, the norm of, let's say, the derivative of psi L, then this would be comparable, for instance, to, let's say if I put two derivatives here, to the frequency omega L squared times psi L, okay? Which you would imagine if you indeed solve an equation of this form with P, which is a second order operator, okay? And localizing space, so imagine that, let's say, the psi L are defined on some, let's say, manifold sigma. And imagine that omega is something in sigma but different from sigma. Then essentially what I want is that I want psi L to be, let's say, 0 on the complement of omega, okay? Something like of this form. Or it might not be exactly 0, but it might be very, very small, and the smallness, you can measure it exactly what it is in terms of L when L goes to infinity. Okay, so this is a very general introduction to these quasimodes, and the reason why I wanted to give you such a general introduction is as to see that this is not a construction which is specific for black holes. This is a construction which is specific for just spectral problems, which has a broad range of applications. It's also a little bit of an old subject. I mean, it started, I think, from maybe the Russian in the late 60s. But we're going to see that it applies very nicely in the case of ADS black holes. Okay, so this is what I want to do here.
In this case, omega, should it be a compact manifold, or it doesn't have to be a
It's not going to be compact, but in some sense it's very similar to compact. In the case of, let's say, the Schwarzschild space, it's going to be the set of all points which lies outside from I equal to n. Okay, from I equals to m to...
Physically saying that something is localized, if it is localized on a non-compact, that doesn't look too localized.
Look,
but that's just a definition.
Yes, it's just a definition. Okay. You can maybe you don't like the word localized. Okay, so just say it has some physical space properties. That's what I meant. Okay. So before I tell you how what happens in the case of ADS, I will also like to show you that once you know that these quasimodes exist, you automatically know a lot of things about the exact solutions now of the original operator you were looking at. So this is not something that, you know, once you've done the quasimodes, you're also essentially finished for the point of view of applications. So I want to do two applications, maybe here. So I want to mention at least two applications. So one application is that if you know the existence of quasimodes, there is a little bit of work to do, but you can often show that they are in one-to-one correspondence. I mean, it depends. It's not necessarily true that it's one-to-one, actually. But okay, for simplicity, let me mention one-to-one with quasi-normal modes. For one-to-one, you need also to know that they don't accumulate somewhere. Okay, so this is not quite true. But let's say in the case of ADS black holes, let's say Schwarzschild ADS, there is a nice paper of Gano which do a quasimodes construction similar to the quasimodes that I have done with Gustav Holzegel, although only in the Schwarzschild case. And from this quasimodes construction, then there is essentially abstract theory from this, the setting of spectral theory, which tells you that you automatically have quasi-normal modes with the properties that you would like, especially the frequency of the quasi-normal, the real part of the frequency of the quasi-normal modes will be close to the real part of the frequency of the quasimodes, and the imaginary part will be very small if the error is very small. Okay. So, and another thing that is very easy to get once you have the quasimodes is you can very easily prove a lower bound on the rate of decay of solution. Okay, so this is so easy that I can essentially give you a full proof on the board. So imagine that you have a sequence of quasimode box of Psi solution to your wave equation. Okay? And say that you just know that the error psi of, just as an example, say that you know that this is a little O of L. Okay? Something which goes to 0 as L goes to faster than as L goes to 0. Let's say I want 1 over L. Thanks. Thanks. Next page. Okay. So what do? I want to page 2, page 1. So what I want to apply is to apply Duhamel formula. Okay, so what does Duhamel formula tell me? It tells me that if I know how to solve the homogeneous solution, the one where I have 0 on the right-hand side, I know how to solve the inhomogeneous solution when I have something on the right-hand side. So what does exactly this formula say? It said that denote, let's say, psi L homogeneous, the solution of box of psi L is equal to 0, with the data, which is the data induced by your solution psi L. Okay, so the data will be psi L homogeneous, let's say at time t equals 0, is equal to psi L at time t equals 0, and the dt of this will be the dt of this. Okay? So I just take the data which is given to me by this function, which I assume I know how to solve, This gives me initial data for the free-variable equation, and then I evolve the free-variable equation. This is the homogeneous solution. And then the Duhamel formula tell me that I can write psi L, the inhomogeneous solution at time t, as the homogeneous solution at time t plus an integral between 0 and t of something which, let's say I can write like this, some chi of t and s, where chi of t and s is again a solution of the homogeneous problem. So again, something that I can easily solve. I need to write something. Okay, so chi s, this will be the solution to box of chi is equal to 0 with initial data which is chi of s is equal to 0 at, yeah, so it's really this, it's chi of s is equal to 0. So which means that I prescribe data on the hypersurface s, t equals s if you want. Okay, so that's a slightly perturbing thing. And dt at s is equal to the inhomogeneous term at time s. Okay? So if you plug this into here, okay, you need two things. You need the fact that this box operator is invariant by t. Okay, and okay, I'm also cheating because you need also the coefficient in front of the GTT to be 1. If it's not 1, then you have to multiply this by the appropriate thing. Okay, but once you have this, you see that it's very easy to get, let's say, an estimate now of the homogeneous solution. Yes? For the moment, this is what I'm saying here, that this holds for any equations. It has nothing to do with any space-time or anything like that. It automatically. Well, if you think of an application in the case of Schwarzschild-AdS, then let's say GTT would be the GTT of Schwarzschild-AdS in static coordinates dr theta phi. It could not even be a global hyperbolic spacetime. Anything that when you know how to solve the homogeneous wave equation, this will hold. Okay. This is the point which I want to make. Essentially, that this quasimode is very general. And then I move to an application.
It's a stationary spacetime.
Sorry?
Is it a stationary spacetime?
It has to be stationary for this to work because I need this box to be invariant by d by dt. Okay? But it could also be, you know, something which like an abstract Schrödinger equation. So sort of.
D by dt have to be time-like.
Sorry?
D by dt have to be globally time-like.
I don't need to have a d by dt which is globally time-like, but I need the fact that in some sense, it is hidden in the fact that I need to know how to solve, how to construct the psi L. And to construct the psi L, I need some sort of ellipticity somewhere. Okay, so it is hidden there, because then if you, the globally time-like d by dt corresponds to the, let's say, the decomposition in terms of, if you think of box to be like equivalent to omega squared minus p, I need the p to be elliptic for the constructions. But if you tell me you know how to construct it for a non-elliptic operator, it will work as well. It's completely, okay? Okay, so imagine that I have a formula like this, and what do? I put the psi L on the other side, and then I have a norm of psi L homogeneous minus psi L, which is less than, let's say, t times the sup of the norm of chi ts, let's say, between 0 and t or something like this. Okay, so just a naive estimate that you could think. Now, here I need something else. I need to know that the solution of the homogeneous problem are bounded by the data. Okay, so if I know that the homogeneous solution is bounded by the data, this is comparable to the norm of this. Okay, so I could say that this is less than t times the norm of phi L. Okay, any phi L is, let's say, of order 1 over L, this is less than, let's say, T over L. Okay? Now, if T, let's say, for T less than L over 2, then I obtain something of the form psi L homogeneous is bigger than 1 over 2 psi L, the real psi L, with no homogeneous, up to T equals L over 2. Okay? Now, this solution is periodic in time. Okay? So this is the same as before. Okay? So far I have done nothing very special. Okay, and imagine now that what are these norms? I mean, I haven't really told you what these norms were. Okay? It was very abstract. Now think of this norm to be like the energy in some domain, omega. So this will be also the energy in some domain omega. But because I have localization in space, this will be the same as the total energy. Okay, simply because the things were 0 outside from omega. Okay, so we have proved an inequality like this. So this automatically tells you that, let's say, if you think of a statement like let's say for all solution, let's say psi to box psi, let's say the energy of psi in some domain is less than delta t times the, so this is a time t, and this is a time t equals 0 of the total energy. Okay, so this will be a decay statement with delta t a function which goes to 0 as t goes to plus infinity. So this tells you automatically that this cannot hold. Okay, simply because you take you take t equals L over 2, you take your psi L, you put it here, okay, and you will find that delta t has to be bounded from below by 1 over half, so it cannot go to 0. Okay, so this tells you something like that. Now, if you have something more about the psi L, if you know found that this error here is not 1 over L, but like exponential of minus L, then this will automatically tell you that using also the fact that you have this localization in frequency, you can replace this energy total by, let's say, second order energy, and then you're using the fact that you have better properties on the f of L, you can, for instance, very easily show that you will not get better than logarithmic decay in a situation where the f of L is like exponential of minus L, okay, by exactly the same argument. So see, it's very general, and it's also not very difficult. Okay, so after all these generalities, let us focus on the case of AdS black holes. Okay, so in the case of AdS black holes, so the result that we originally obtained with Gustav was the following. So this is work of Gustav Olsegal and myself. So you take, let's say, so this is the domain of outer communication over Kerr-AdS black holes. So there are some conditions on the parameter. Okay, so this is the angular momentum per unit mass. This L here is related to the cosmological constant, so it must be something like this. R plus is the location of the event horizon. So there is also a condition just to get a regular black hole. And finally, we will look at the equation, which is the Klein-Gordon equation. And I need the Brighton-Lerner-Friedman bound to hold. Brighton-Lerner Friedman bound. Okay. So what we proved was that the solution, so this is, let's say, the Klein-Gordon equation. To the Klein-Gordon equation satisfies an estimate of the form the first order energy is like 1 over log T star times a second order energy. Okay, let's say for all T star, let's say bigger than I guess 2. Okay, so here say that okay the T star equal constant slices are regular slices of the event horizon. Okay, and so the point is that so this is a theorem which we had proven some years ago, and that with this quasimodes construction we can prove that this estimate is sharp in the sense exactly that I mentioned before, that let's say so the theorem which we now have I could write it here in the sense that okay, so let's say star is sharp. Okay, so by this I really mean that the statement let's say there exists some function delta of t which goes to 0 such that for all psi solution the first energy of psi, let's say, divided by the second energy, let's say non-zero. The second energy of psi times log of t star is length that delta of t star. This statement is false. Okay? And what it means that the statement of the left is sharp. Let's say that you cannot improve it by improving the decay rate.
All of this in any ADS, any asymptotically ADS.
No, Kerr-AdS.
Okay.
Okay.
Asymptotically curved.
Kerr-AdS.
Dimension.
Sorry?
Any dimension.
So we proved it in 1 plus 3. Okay.
So it's ADS per ADS 4.
Kerr-AdS 4. Okay. So let me make just a few comments about both the Stage theorem and the theorem 2 and theorem 1. So let me first say, of course, that the equation that we are looking at, this Klein-Gordon equation. Okay, so this equation is well posed. And here I have to mention what type of boundary condition I'm looking at. Okay, so here it's theorem 1 and 2. Okay, are concerned with Dirichlet boundary condition and homogeneous Dirichlet boundary condition. Okay, so psi is equal to 0 on the boundary in a rescaled norm. Okay, and let me mention that, of course, so this well-posedness, okay, there has been lots of work on it. I could mention, of course, the origin work of Brighton, Lerner, and Friedman. There's the work of Isibashi and Wald, of Vadi, Bachelot. Okay, and using vector field method, there is a work of Gustave Holzhegel. And if you want to study more general type of boundary conditions like Robin boundary condition and things like that, then there is this more recent work of Claude Warnick on it also. Okay? So here we are only concerned with the homogeneous Dirichlet boundary conditions. And this type of statements depends on the type of boundary condition that you're looking at. Okay. Let me also mention that, let's say remark 2 is that prior to our work, there was also a boundedness statement, which simply says that you can control your solution up to the event horizon, okay, let's say in the energy of the solution by the initial energy of your solution, okay, without the log T decay. So this original work was done by also Gustave, but it turned out that we actually need this statement for the proof of our theorem. And in the original proof of Gustave, there was some restriction of the parameters, which was later removed in work of Holzhegel and Warnick. Okay, so if you want the full range of parameters, then we need to appeal to this work.
Maybe I'm just asking. So if I am to compute quasi-normal modes, right? So one boundary condition, as you said, you have to impose, and you impose Dirichlet boundary condition. That's the asymptotic boundary, but you have to say something about what happens at the horizon, right?
The function is regular. Take a regular set of coordinates at the horizon.
Right, but usually you have incoming and outgoing modes, right?
You don't. In this case, just think of the horizon is your function is defined on the whole space. Okay. So the fact that you have to impose ingoing and outgoing, let's say, to select what you want in the horizon, this is only due to the fact that the event horizon is singular in the set of coordinates that one typically is using. But in reality, it's not really singular. We all know that there is a regular set of coordinates.
Yeah,
okay?
Absolutely. But I'm saying that the spectrum and
it's independent of this, because if I want to know what
that's what I wanted to hear. So you're saying that it doesn't matter how I impose a condition at the horizon,
as long as it's a regular condition.
As long as it can be a superposition of ingoing, outgoing,
yes.
It would still, all of this would still.
But this is really just a fact about the domain of dependence, that the solution here only depends on what's here and what's here, and doesn't see at all what's outside of here.
Okay. Just one second, just to make sure I understand. So what you prove in this theorem basically is that if you have high angular momentum, the solution is bounded. So because it is very difficult for the solution to tunnel, because there is a huge barrier.
It's actually not exactly. If you check just one solution,
yeah.
Okay, with high angular momentum, it will still decay. If you have only one, it will decay. In fact, in the Schwarzschild case, we prove that it decays exponentially. Okay, but what happens is that if you, I think it's enlightening to see this maybe once. Okay, if you just take one mode solution, what you can prove is something like this: that the solution will decay exponentially. The trouble is that this constant here, it will decay, sorry, it's something like this. Okay? The constant here will decay exponentially itself.
Yeah.
Okay? So when you take a superposition of many, many modes, then you completely lose the structure. Okay, but as long as you look at just one mode, you will actually never see any trouble, in some sense. Okay, so the last thing which I wanted to mention is that this, this restriction on the parameters, this is just to get a regular black holes, but this one, on the other hand, is you could violate it a priori. This is the Hawking-Real bound. Okay, so I'm not sure if there is the random one. Okay, so this you could try to violate this bound, and in fact, the statement about the quasimodes does not need this bound to be true. Okay, it's just that when this bound is not true, one expects that at least for some parameters, one can construct solutions which actually are not bounded. So, just proving that the solution do not decay faster than 1 over t is a much weaker statement than the exist growing mode. So, Okay. So let me now, okay, I have 25 minutes. Tell you about how do I construct these quasimodes. Okay. So essentially, you will see that in the Schwarzschild-DS case, it's not so hard. In the Kerr, it's of course essentially any statement much harder. Now, everything we've done is for 1 plus 3-dimensional black holes, but the method, I mean, I think it extends very easily to higher dimensions. I mean, not to say that there is nothing to check, but let's say constructions of quasimodes. Okay, so first you use your favorite separation of variables. Okay, and you rewrite things in the following form. Okay, so what do I write here? You started with a solution of your, let's say, Klein-Gordon equation. And then, let's say, if C was a solution to box minus alpha over squared C equals 0. U is just the usual rescaling of psi. Okay, and then I've done a Fourier transform in time. Okay, prime denote d by dr star derivative. Okay, let's say this is what is it again? It's I have to make sure dr star by dr is 1 over okay, so say I start with Schwarzschild-DS case because it's a lot easier. Schwarzschild. Okay. And I do it also, so let me put some L everywhere here because I do a spherical harmonic decomposition. Okay. And I've rewrote the potential that you get after you do this decomposition in 2 pieces, okay? One which I call V-junk, which doesn't contain, so LL plus 1, okay, these are the eigenvalues of the Laplacian on the sphere. So what doesn't contain it, I call it V-junk, and the other right, I call it V-sigma as the main part. Okay, so V-junk is actually not completely negligible even at high frequencies because of the behavior near infinity, but let us neglect this for, just for the point of view of the talk, okay? So what I really want to think about for simplicity is just this. I want to forget about this and just think about an equation like this. Okay, and then I want to think, I want to divide by LL plus 1. Okay, so what I want to do is essentially this. And I want to think now as I want to think of 1 over LL plus 1 as a small constant, let's say h squared, and I want to use relatively standard semi-classical analysis. Okay, so omega squared over LL plus 1, I want to think of this as being an energy level. Okay, and this is my semi-classical parameter. Okay, now what does V sigma look like? So essentially, V sigma looks something like this. So this will be the boundary of, the boundary to infinity of Schwarzschild-DS. Say this is an R star, okay, a graph. This would be, let's say, r star going to minus infinity, it's the location of the event horizon. Okay, and V sigma looks something like this. Okay, so this is 1 over L squared. And the top here is exactly like in Schwarzschild, it's the photon sphere at I equal to m. So what I want to do now is I want to fix an energy level somewhere here. Okay? Okay, so I want to think of it as my energy level. And I want to consider a Dirichlet problem, completely artificial, Dirichlet problem. So it's an artificial, it has a priori nothing to do with any physics. Okay. In which I will impose Dirichlet boundary condition, okay, at infinity, like I usually do when I solve the wave equation with Dirichlet boundary condition in AdS, but also at r equal to m, okay, which in some sense is artificial. Okay, so I impose boundary condition here and here, okay, and I want to solve an eigenvalue problem. Okay, and the eigenvalue problem which I want to solve is essentially minus h square u prime prime plus v sigma of u is equal to an eigenfrequency depending on h times u. Okay. Now, what I really want, of course, is I want this energy level E of h to be somewhere which is below, let's say, the top of my potential, so that at least at the classical level, the particle which will be here will be trapped. Okay, between the potential and the boundary at infinity. Now, of course, I cannot just say, well, there always exists a solution here with EH. Okay, I don't know this, but what you can easily prove is that at high frequency, if you give me, let's say, fixed E, then there exists, let's say, a sequence U of h and E of h of solution to, let's say, my eigenvalue problem, and such that the frequency E of h converge to the fixed frequency which I want as h goes to 0. Okay, this is easy to prove. Well, not super easy, but one can prove this. Okay, so I do not know that. Okay, I cannot say I have a solution here, but I know that there is a solution very close to any fixed level that I give myself. Okay? Okay, and so once I have this, I need another piece of information. Once I have constructed this, I want to know how is the difference, let's say, how is my classical behavior differs from my real behavior, which means I want to quantify how much energy can go through this tunnel. Can go through this potential via tunnel effect. Okay, so in elliptic estimate, there is a well-known procedure for doing this, which you can apply in this case. Okay, so I can define, let's say, so this is, let's say, step 1. Okay, the Dirichlet problem is step 1, and then step 2 is quantified tunnel effect. Okay, and you first define what you call the forbidden region. Okay, so this is, let's say, the set of all R star, such that your potential is bigger than your energy level. Okay, this is a region in which classically you cannot enter, so the forbidden region. And what you can prove is that then the size of your solution U in the forbidden region is less than E to, let's say, some constant times H, or 1 over H. And this is the total norm. Okay, so it becomes exponentially small in 1 over h as you enter the forbidden region.
In what regard is this different from WKB?
So WKB, you reconstruct a solution by finding an ansatz, okay? And then you plug it into it and you construct a series, okay? And then what you hope is that this series essentially converge or represent well what you're doing. But here it's not at all what we are doing. We are not taking any ansatz, okay? Or if you want, we are saying that one very good ansatz is a solution to this problem, but which we do not know exactly what it is. It's just an abstract solution. I have no idea what. The only thing I know about it is I know how to prove qualitative behavior, but I do not know how to construct it by hand. Okay, and then once you have this, step 3 is very easy. Okay, so you could think, okay, what about now just taking the solution U, okay, as my quasimodes? Okay, it's defined only up to I equal 3m, but I could try to extend it to the left, okay, up to the horizon. The trouble is that if you do this, you should end up with a mode solution. But you know that you can prove that there is no mode solution on Schwarzschild-AdS. So the only thing that should happen is that the solution will be irregular at the event horizon, okay? And as we mentioned before, the solution is actually regular at the event horizon. So how do I get a regular solution to the event horizon? Well, I'm going to exchange the fact that it's an exact solution to get more regularity. So I'm going to cut off the solution here smoothly. Now the solution will be just 0 there. So this is the localization in space. Okay? But on the other hand, it's not going to be a solution anymore because the cutoff will introduce some error. So this is step 3. So step 3 is, I don't want to write anything wrong. Okay, it's cutoff. So you want to consider for your quasimodes psi L, let's say, of T R theta phi, which is going to be simply e to the I. So if I don't say anything wrong, is this times L plus 1. Okay, so remember that E of L was, or E of H, if you was omega squared over LL plus 1. So omega squared is E of L times LL plus 1. So this is what I've put here. Okay, so time t. Then I'm going to have my U of L, which depends only on R. Then I have to remultiply this by R, and then I have a spherical harmonic. Okay? So this is the ansatz, this is the quasimode that you are looking at, except that, again, this solution will not be regular. This is a mode solution, so I have to cut off. So I'm going to multiply this by chi, let's say of R, where chi of R. This is equal to 1, let's say, for R bigger than 3m plus delta, where delta is going to be small. And it will be 0 for R less than 3m, okay? And it's smooth. Okay, so delta is small compared to what? So delta is small so that what you want is that in the region between 3m and 3m plus delta, you want this estimate to hold, okay? So what you want is that you have to choose delta sufficiently small so that the forbidden region is between 3m and 3m plus delta. Okay. And then you have exactly what I mentioned, which is that box of, let's say, box minus alpha over L squared of psi L, okay, then is equal to f of L. Okay, so what is f of L? Well, outside from the region where you do the cutoff, f of L is 0, because there is no error. And within the region where you do the cutoff, f of L is exponentially small, thanks to the estimate which we wrote down here. Okay? So, not very difficult. Okay, so this is for the Schwarzschild case. But now I want to tell you just some ideas about how do I extend this for the Kerr-AdS case and why this is harder there. So, in the Kerr case, the Kerr case, it turned out that step 2 and step 3, that is to say both the exponentially small estimates and the reconstructions, they are done exactly the same. There is no problem. Okay, so step 2 and 3, fine. What is difficult is step 1, and this I will explain. So, okay, so recall that in the Schwarzschild-AdS case, let's say Schwarzschild-AdS, what you solve is something like this: 1 over LL plus 1 times u prime prime plus v sigma times u is supposed to be equal to some energy level associated to L times u. And then you think of omega squared of L to be just E of L times LL plus 1. Okay? Now, what is LL plus 1 here? LL plus 1, this is the it's eigenvalue of the Laplace on the sphere. Okay? But we all know that if you want to apply separation of variables on, if you want to do separation of variables on Kerr-AdS, you do the analog of the Cartan separation of variables on Kerr, and you have to replace the Laplace on S2. You have to replace it by an operator, say some P on S2, but which is now going to depend on the time frequency. You first have to take Fourier transform in time. Once you've taken Fourier transform in time, you have an operator on the sphere, and this operator is nice, apart that it depends on omega squared. Okay, so it depends on omega squared, but as the rotation parameter goes to 0, it reduces to the Laplace on the sphere. Or so I will add an A here. Okay. Okay, so you could do still the same thing, and you will end up with a priori the LL plus 1. These are replaced by the eigenvalues of this say oblate. Essentially, in the Kerr-AdS, it's not even an oblate spherical harmonics, but it's close to it. So this will be replaced by a frequency, let's say lambda, which depends on L, M, and let's say A omega. Okay. So M here is frequency associated to the invariance by d by d phi. Okay, L is an additional frequency parameters on the sphere, and A omega is as before. So to do the construction, we can just reduce ourselves to the case M equals 0. Okay, so we are only going to look at axisymmetric solution. So I'm going to look only at lambda L0 and A omega, and I will call this mu L of A omega. Okay, now once I know how to do this decomposition on the sphere, I can plug the same thing, and I will obtain an equation which, as in the axisymmetric case, it's easy. I will obtain 1 over mu L of A omega times u prime prime plus a new V sigma which depends on A, but let me not write this explicitly, times u. And this is supposed to be again equal to some frequency applied to u. Okay, so this is the eigenvalue problem which I want to solve. The trouble is that, okay, the semi-classical parameter depends on omega. But how was omega defined before? Well, omega was defined in terms of the solutions. Okay, so it is not a regular eigenvalue problem. It's a nonlinear. It's a nonlinear eigenvalue problem. Okay, because if I want to find if I find a frequency E, I cannot rewrite it now as omega squared times mu L A omega. Okay, or I need to find the eigenvalue before I actually solve the problem, convolute problem.
You sigma is still of the barrier form.
Sorry?
The phi sigma out there.
Yes.
That's still similar as
The phi sigma, it's similar, but it actually depends on A, so it's slightly modified as well. But it has a similar behavior to the one which I wrote earlier.
still like a tunneling problem, but now
Yes, yes. It has similar properties, but okay. So what do you do to get around this nonlinear? Yes, it's very good because I have only one page. So how do you get around this nonlinear eigenvalue problem? Well, you have to use nonlinear, let's say, techniques. Okay. So what we use is an implicit function theorem. So I can maybe write this here. Okay, so for each L, we're going to define an operator. Okay, so our aim will be to apply the implicit Fontan theorem. So we define an operator. Let's say it's a family of operators. Okay, so consider the following family of operators. Okay, so these operators will depend on A and on omega. Okay? So the operator is the following. Okay, so you see it's what you obtain if you were to write this as being mu L times omega squared, and then put it on the left. Okay? Then you obtain this thing. So in particular, if this has a 0 eigenvalue, then you have a solution to your original problem. Okay? So what you want is 0 eigenvalue of QL of A omega, our solution to the nonlinear problem. Okay, but there is nothing which guarantees to you that this indeed has a 0 eigenvalue. What you do know is that when A is equal to 0, okay, you know that at omega is equal to the frequency that you find earlier solving your Schwarzschild problem, then you know that you have a 0 eigenvalue. Then 0 is an eigenvalue. Okay? So what you do know is that you know what's going on for the Schwarzschild case, and you're going to essentially differentiate with respect to the parameters so to transport this information. So that's what you want to do. So how do you do this? So this, say that the solution that you have found earlier, it is the nth eigenvalue of this operator. So below this, I have negative eigenvalues, and above I have positive. Okay? So say it is the nth eigenvalue. Then I want to define the map, let's say lambda L of A omega, which gives the nth eigenvalue of the operator QL of A omega. Okay. And now I know that lambda n of, let's say, A omega L is equal to 0. Okay, and I apply my implicit function theorem. And what I want to obtain is that lambda n of, let's say, A omega A is equal to 0, okay, where omega now is a function of A. Okay, omega A is going to be a regular function of A. Okay. So this is essentially what you want to do. Now there is 3 obstacles for this. Okay. So in order to apply the implicit function theorem, you need to know that when you take derivative of this map with respect, first you need to know that this map is regular. Okay. Then you need to know that when you differentiate this with respect to omega, this is non-zero. Okay. And then one of the last things that you need to know is that the implicit function theorem normally it's a local construction. Okay. It tells you only that there is a small neighborhood of, let's say, A equals 0 for which you can apply something. So if you want to extend this to a whole neighborhood up to, let's say, A is equal to this maximal value, then you need to prove that every estimate that you need here is uniform. For instance, you need to prove that the derivative of this with respect to omega is uniformly bounded from below by something which does not degenerate as A is moving. Okay? And finally, there is a final step which is also quite miraculous. You need to prove that once you have done all of this, the frequency that you find, which is going to be essentially E of A is going to be the omega squared of A that you have found by mu L of A omega A. Okay? This is your energy level. you need to prove that this energy level, which a priori you do not much about it, you need to prove that it is still below the top of the potential. Because it could be that, okay, you have found a solution, but maybe this solution now has jumped and is very high in this energy level, okay? And it turned out that there is a monotonicity behavior. So what we found is that it was not the best idea to start with the A equals 0 case to be the Schwarzschild case, actually. We introduced a small modification to this operator so that at A equals 0, it does not we kept part of the you see this potential V sigma, it depends on A priori, and we made it constant in A in some sense. So when A equals to 0, what we found is that we only vary the mu L of A omega. And doing this, you can prove that this energy level can only decrease. And if it can only decrease, or almost, I mean, there is a small epsilon, but opposed to this small epsilon, it can only decrease, which means that you will stay below your top of the potential. Okay, I will stop here.
Unique question. Yeah. Ask a question. So,
Sure.
so this is where this can be applied. I guess if I'm a person who wants to use some of the would, for example, something maybe I don't know, maybe it's completely unrelated, but the questions that I always had is whether if I have a quasi-normal modes and I compute not in an approximation or sort of a model, how you were defining it, you know, basically Dirichlet, but real quasi-normal modes with imposing either ingoing or outgoing boundary conditions. Do they form a complete set?
So
would that any
no, they will never form a complete set. I mean,
is that true? I mean, this is, you know, I've heard various.
Claude will
Talk tomorrow.
Okay, okay.
But no, I mean, the typical thing that you have is that if you have a general solution, the one typical behavior, which is not proven in all cases, but it's proven, let's say, for Schwarzschild de Sitter, and I think one could do the same for Schwarzschild-ADS, although it has not been done yet. If you have a typical solution to the wave equation, you can write it as a sum of quasi-normal modes, okay, plus a remainder, but the remainder will typically be there. And what this remainder will be, it will be something which will decay much faster than all the quasi-normal modes, typically exponential of exponentially fast. So it will be very, very small, but nonetheless it's present. But you could think that presumably for physical application, this remainder is at least at large time quite negligible, I would imagine.
Okay, but
Okay.
I'll wait.
Just following his question. So that means that, let's say that you put some energy on ADS. So what you're saying is that there are some type of quenches in which you don't see a relaxation, right?
Well,
In some sense, because you have this barrier of
you have this barrier, but there is still a form of, I mean, if it's only a scalar field, which is linear, then there is still some decay, just it's a very slow decay. I mean, on top of it, I guess if you really wanted to make a statement about a physical system, you may have to actually compute whether it's exponential of minus CL, what the C is here. Because if the C is very, very small, maybe at some scales which is interesting, you might see either nothing or everything. I don't know.
Even a more general question. So I listened to it. It's basically, it's kind of a tunneling problem in general, right? At the moment you go non-linear, that's something special. I can repeat the question. Normally we do WKB or even less than that. We just take solution on both sides of the barrier and match them. And this seems to be kind of a generalization that is more flexible, whatever. Where is the advantage? Why is this better than?
So I think if you wanted to do WKB here, what you would, I would think you can do it by WKB, but you have to be very careful, and I think the analysis would be much harder for the following reason, that WKB, you typically have a series, and then you have many, many error terms, and you have to essentially show something for all these error terms. The trouble is that if you really want to get an optimal result here, you have to show that the error is exponentially small.
Yeah.
Okay, and exponentially small is not that easy. I think by WKB, what you would presumably get is, if you do it, let's say, and after n iteration or something like that, you would get maybe faster than L to the minus some power. Okay, and then often in the math literature, you find that you can extend this to faster than any polynomial, but then there is still a little bit of a gap between faster than any polynomial to faster than to exponential. So, but this is this construction like this would not have worked for let's say just Schwarzschild, not Schwarzschild-AdS. There you would need to do either WKB or there's also a paper of this of Jan Zbierski using Gaussian beams, something different. But the idea, what is I think nice about this, is to do an approximate solutions. And why is approximate solution nice? Is because if you change a bit the operator, it's still an approximate solutions. You only have to compute whether the error is big or is not so big. Okay, and it's very easy to obtain. I mean, for instance, you add to this V sigma any type of small things, then the proof is exactly the same. There's no difference. It's completely automatic. It's very easy.
Can you dream of typical quantum mechanical tunneling problems where this would be superior? I mean,
well, so for the people who do, let's say in quantum mechanics, if you want to measure to really measure this, let's say when you want to confine a particle with a potential, then they use this exponential decay of solution in the part. I mean, this is all their papers.
Yeah.
Okay, and they don't do WQB in this case.
Right.
And this is how we found out about it. Just that I don't think it had been seen that this had also application in the black hole case.
So unless there are any more urgent questions, let's then